So that's the goal of the RAG system. When you have this, you can then having a system that is able to answer in natural languages questions about your private data. So this is more or less the diagram. From the left to the right, we have the question. The question goes to the database part, and the database provides you a set of results. Typically, give you a list of results with a score. So when you have this subset of documents, you can then combine this information plus the question. So as you can see here, the same question is driven to the database and after sent to the LLM. So basically the LLM gives this big question as input and is able to, because LLM speak natural languages, they are able to get the knowledge of these documents that was retrieved by the database and provide you an answer in natural languages. Okay, so thank you again for having me. My name is Enrico Zimmer. I work for Elastic, and today I would like to talk about Retrieval-Augmented Generation for talking with your private data using LLM. So very long title. The goal is to show you how it can be simple actually to create a RAG system using mostly open source technology. So this is the agenda of the presentation. So I will introduce the RAG system. I will talk about semantic search and vectors, embeddings, vector databases, how to manage documents to insert this document into a vector databases. I will talk about LangChain. This is a very exciting project in Python and JavaScript to build application using large language models. And last but not least, I will try to do a demo, because I say try because every time that I'm on stage, the Murphy law came and something was wrong. So please cross your finger. Okay, so a few notes about me. I'm an old developer, 1996. I am an old open source contributor. I also contribute to LangChain recently. I work for Elastic. I was a researcher at the University of Amsterdam. I am an adjunct professor of the University of Torino and ETS Piemonte of Torino, trying to teach programming. I also had a speech, a TEDx speech about creative programming long times ago here in Turin. And I wrote a couple of books. And actually, I'm writing now a new book, and I'm using intensively ChatGPT 4. And I did an estimation. If I, in the past, spent almost 1 year to write a book, right now I can write it in 2 or 3 months. So that's very huge improvement for me. Okay, let's focus on the RAG system. RAG, again, is Retrieval-Augmented Generation. It's basically a technique that enables you to improve the knowledge of large language model without retuning the model itself. So it's a way to expand the capabilities of large language models. It's basically composed by 2 parts, the retrieval augmented part and the generation part. So let's focus on the generation part first. So as we know, large language models like ChatGPT are a disruptive technology. Everyone is talking about it, everyone is abusing it, everyone is everywhere. They're very powerful, and right now we just scratch the surface of what we can do with this system, because now it's like the far west moment in the industry. Everyone is trying to do everything. So it's very, very, early time for this, but it's very, very exciting because you literally can invent the next big thing with this kind of stuff. But underline a lot of time, please. There are some limitations. First of all, no source. If you give an answer from a LLM, you don't know where the answer came, basically. There is no evidence of any source. And this, most of the time, technically, we know this is called hallucination, because this kind of model always try to give you an answer. So you have to, limit in some way the model. So this is a big issue. So we don't have any system right now to verify the information that are coming from LLM. And other limits, it's the out of date, because these systems are trained, and it took a lot of money and a lot of time to train it. As you know, OpenAI is spending billions of dollars for training this model, and that's why you see ChatGPT 3, ChatGPT 4, ChatGPT 5, and so on. So the idea is, if you want to update a LLM, you need to retrain, and this is quite expensive. So the retrieval-augmented part of these techniques is the ability to basically collect a set of public or private data. So imagine that you are a company, you want to store your private data, so you don't want to send this data to a cloud system like OpenAI for privacy, for any kind of restriction. But you need to build a kind of retrieval system, so a database, more or less, where you put this information inside. And you want to get back this document using a question. So you don't have a SQL. You cannot write select a star from whatever, like blah, 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 right? So you want to have a system that is able to send a question to this kind of databases. And this is called semantic search. So you need a system that is able to give you a semantic search. When you have this, you can then combine the power of semantic search plus the LLM, and having a system that is able to answer in natural languages questions about your private data. So that's the goal of the RAG system. So this is more or less the diagram. So from the left to the right, we have the question. So imagine you are giving a question about your private data. The question goes to the database part, and the database provides you a set of results. Typically, this kind of databases for semantic search give you a list of results with a score. Score is a number that basically is the quality of the connection with the question. So if the number is higher, that means the document is relevant for that specific question. So it's not a way to answer the question, it's just a way to find the right document that contains the semantic of the question itself. So when you have this subset of documents, you can then combine this information plus the question. So as you can see here, the same question is driven to the database and after sent to the LLM. So basically the LLM gives this big question as input and is able to, because LLM speak natural languages, so that's the idea, are very good to speak natural languages. So they are able to get the knowledge of these documents that was retrieved by the database and provide you an answer in natural languages. So in order to build this RAG system, you need a semantic database plus an LLM. That's the idea. Okay, but what are these semantic search databases? We have a lot of examples in the industry, but recently one of the best technology that came out was the vector databases. And everyone now is talking about vectors. So what is a vector? A vector is a set of numbers. So everyone with a degree in engineer knows what is a vector, unfortunately, because spend a lot of time breaking heads in analytics and etc. Anyway, we can simplify stuff here and say it's just a set of numbers. So for instance, we have a vector of 3 elements with these 3 numbers, 10.5, 11.23, and etc. Of course, this is just a simple example with just 3 numbers, but when you put information inside this system, the vector is quite long. Typically, it's 1K elements. And technically, this is a multidimensional space. So here there is a very simple representation of two-dimensional space on the left. So x and y, this is the point 1.1. And in a three-dimensional space, we have basically three elements, x, y, and z. And this is the representation of the elements. So we are talking about numbers. So inside a vector database, there are numbers. Okay, but why we need to talk about numbers? Because, we need to apply models, mathematical models, neural network models. So we need numbers. And how we can check if two numbers are close to each other? This is the idea of similarity. So we need to define a way to compare two vectors and say, these two vectors are close to each other. That means the semantic representation of the vectors are close to each other, whatever semantic means. So we need to define a way to measure this similarity. And there are a lot of proposals here. I don't want to, for who is not technical, I don't want to discourage you with the formulas, etc. But this is just a list of possible ways to represent similarity between two vectors. So basically, we can measure the angles between two vectors. If you think about vectors as lines, we can model the closeness using the angle. You can measure the Euclidean distance. You can do more sophisticated stuff like dot product and etc. This is just a way to see, starting from two vectors, if they are similar or not. The nice part of this is a formula. It's a mathematical formula. So you don't have anymore to do crazy stuff like in the database, structured database like inverted index, searching for all the string, comparing with regular expression, this kind of very intensive CPU stuff. In vector databases, a query is a mathematical formula. So it's beautiful. It's very, very fast. But wait a moment. You told me at the beginning that I have to take documents, and how I can put a document inside a vector database. Of course, I need to translate it in numbers. And this operation is called embeddings. So embeddings is a way to translate any kind of information, like a string, a document, like an audio file, like an images, into numbers, into a vector of numbers. There are many ways to do this, but if you want to use LLM, you need to take basically the same idea of the LLM. So you have to use the model itself. So we are talking here about neural networks. That's why also embedding for this kind of LLM can be a little bit expensive, because you need the model that you want to use at the end to translate the semantic of the information into a vectors. So the goal of the embeddings, of course, is to provide semantic. It's not like a random algorithm that puts a document with random numbers. So the numbers, the semantic of the knowledge should be in some way managed. And there are, again, a lot of possible examples here. For instance, if you take a string like grandfather, man, adult, woman, girl, etc., and you put on two axes like age and gender. So the x-axis is the gender and the y is the age. You can, as you can see, collect together piece of information. So the boy, the grandfather, the man are close to each other. The woman and the girl are close to each other, and etc. So the key idea here is to find an embedding models that translate the semantic of the information into cluster of information in a multidimensional space. Okay, what kind of technology right now we can use? There are many vector databases out there. So in this slide, just provide a list of this. One is ChromaDB. It's a recent open source project driven by the Python community. There is Elasticsearch. Of course, this is the database that I'm working on in Elastic. Viviet, Quadrant, Postgres, even Postgres. I don't know if you're familiar. If you already have a Postgres database in your business, you can use the extension, the plugin PG Vector to enable vector search inside PostgreSQL and etc. Again, the list is very huge. So basically, the idea here is, again, using natural languages to query a vector database. So the question that I'm interested in, I want to use the same question to query the vector database. And the query produces a set of relevant documents ordered by a score, what already said. So the idea is to extract a subset of this document. Of course, we cannot have, I don't know, 100 documents and put this document into an LLM, because if you are familiar with LLM, they are limited in the input space, in the number of tokens that you can pass to the LLM. So we need to find a smart way to extract the most significant documents and send it to the LLM. For instance, top 3, top 5 is quite a standard. And the prompt, at the end, the prompt that we give to the LLM is something like, given the following context, where context is the string of all the documents that the vector database found, please answer to the following question. So very simple prompt engineering here. Of course, we need to elaborate the document, so we cannot just get all the documents inside the vector database. Again, because there are some limitation about the size. So we need to chunk the documents. That's a process very common in RAG system. So you need to split the document into subset of information. For instance, if we are using GPT 3.5 Turbo, it's quite common model used for building this kind of application nowadays. There is a limit between 4K to 60K token input. So this is very important. If you need to build a production system, you need to be sure that your documents are fitting in this space. But how we can split the documents? Just splitting in a straightforward fashion way. Again, there are a lot of examples here. One of the most used is the text splitting using an overlap. So this is a document that I take from the European Parliament. It's about Artificial Intelligence Act. So it's a regulation. It's a proposal for regulate the artificial intelligence, quite recently in June of this year. So imagine that we want to store this information inside a vector database. So we need to split the document into chunks, I said. So for instance, this is the first chunk. This is the second chunk. And as you can see, there is an overlap between the two chunks. And this is very important. So this is a parameter that you have to pass to the model of RAG, because why we need to have overlap between the two documents? Because potentially the information that I'm looking for in the sentence is between chunk 1 and chunk 2. So if chunk 1 contains a part of chunk 2 and chunk 2 contains a part of chunk 1, there is a chance that the meaning remains solid. So I'm not splitting the meaning of a sentence, and the information that I'm looking for is splitted into two documents, so the model is not able to get it. So overlapping is a good way to solve this problem. I mentioned LangChain. It's an open source project, very popular. It's impressive. I never seen a GitHub repository like this. And I come from Elasticsearch, that is quite a huge repository. A lot of features. Recently become a startup with a lot of millions founded, just to work on the open source repository. now they are working on, of course, also on the business part. But again, it's a very, very exciting project. It's for Python and JavaScript. So if you want, you can choose your technology that you prefer. And this is actually what they are working on right now. So not just the library, but also shipping feature for debugging, for instance, LLM application. This is a very interesting question. So how we can debug an application like this? Because there are a lot of, as you can imagine, a lot of movement, a lot of Ps, a lot of API calls. So it's quite challenging to debug and monitoring an application running on this model. So they build LangSmith, that's the first in the top of this diagram. This is a way to introspect the monitoring of all the API calls and give you a dashboard to understand the stack trace of all the information. And they're also starting to think about production system, because you cannot put this stuff on a virtual machine with Python running and that's it. So it's not scalable, right? So you need to understand how to scale this kind of application. Okay, I don't want to bore you with more slides, and I want to focus now on a demo. Again, please help me crossing your finger. So what we are going to do here is use LangChain, ChatGPT, and Elasticsearch as a database vector. If you are interested, and you will have the slides so you can get it out, I put a Colab example, so you can try at home if you want. Okay, so let's see if this is working. So first of all, I want to show you the document that I'm using for this presentation. Again, this is the Artificial Intelligence Act. It's a PDF file that I get from the European Parliament. As you can see, this is the date, June of this year, the date of release of this document. So if we ask to ChatGPT 3.5, what is the, sorry, I cannot write, the Artificial Intelligence Act of EU, intelligence, sorry. Quite difficult to write with a keyboard. So ChatGPT is telling me, at my last knowledge updated in January 2022, so ChatGPT 3.5 didn't know about this document. The European Union has proposed a draft regulation, blah, blah, blah. So it's trying to give me an answer, but this document is not present in the model itself, right? So I want to prove that I'm not cheating here, okay? So let's now go to this example. Unfortunately, I don't know if you can read the end of the room, but anyway, you can double check at home. So basically, what I'm doing here is just installing some dependency. So this is a Python code. So if you are not a Python developer, don't worry. Very simple stuff. 100 lines of code, no algorithms, just calling some function. That's it. So I'm installing all the dependency. Here I'm just getting some API key, because again, we are using OpenAI, so we need the API key for sending, for using OpenAI. We are using also Elastic Cloud, so Elasticsearch, so API key for Elastic in this example. And we are using the LangChain project. So just to give you an idea about what is embeddings and how this model works. So here we have 3 sentences in English. I like dogs, I like cannons, the weather is ugly outside. So very simple sentence in English. And we want to create embeddings. So this is the query the function that we need to call it. And an embeddings for this OpenAI embedding model is 1,536 elements. So it's quite long vectors. And this is an example of the vectors. So imagine now that we want to compare this vector to each other. So each vector represents the sentence. Let's try to do, for instance, a dot product. That is one of the most used methodology to see if the two vectors are similar or not. This is what happens. So if we do embedding 1 and embedding 2, again, embedding 1 is I like dogs, embedding 2 is I like canines. From a semantic point of view, these two sentences are close, right? They are talking about the same topics, right? In fact, the results of the dot is a number between 0 and 1. If it's close to 1 means they are more similar. If it's close to 0, are not similar at all. So the first two, the result is 0.996. So quite good results. That means they are very, very similar. If we do the same with sentence 2 and sentence 3, I like canines and the weather is ugly outside, are two, not similar topics. In fact, the number is lower, 0.7, and etc. So this is just to give you an idea how internally this vector database works. It's just, if you do a query, it's just a lot of calculation. So it's very, very fast. And thanks to the GPU now that we have, I recently checked on Alibaba. Who is using Alibaba? Okay. You can find a piece of good Chinese products on it. And there are a lot of GPU with very, very low price. And I'm trying to do some experiment at home just to have some fun. Anyway, it's very nice, this approach, because it's not, the information retrieval is translated into calculation. So this is very, very mind-blowing if you come from old SQL databases. LangChain provides you a lot of utilities to load documents from online websites, from Wikipedia. There is a plugin that is quite fascinating where you can get a YouTube video, extracting the audio of the YouTube video, translating the audio into natural languages with one line of code. So, incredible. Now I'm not doing crazy stuff, I'm just reading a PDF. So the PDF, the document that I show you, I want to take this PDF and put into Elasticsearch. That's the idea, using, of course, embeddings. And the document is 12 pages, and this is just an output of the document. Okay, now it's the moment to split the document into chunks, right? So we need to take this giant document and split into subset of characters. Again, we can use LangChain. There are a lot of methodology here. I'm using the recursive character text splitter. Very simple. The algorithm that I showed you earlier in the slides. So I get the chunk and I get the overlap. And now we have 62 documents. So we started from 12 pages. Now we have 62 chunks inside the vector database, inside Elasticsearch. Of course, now we need to pass this information to Elasticsearch. Again, using LangChain, there is a plugin that we built for connecting to Elasticsearch databases. As you can see here, I'm just passing the splits. That is a collection of all the chunks that we built, the embedding model, and the name of the index. If you're familiar with Elasticsearch, index is kind of a table, more or less, in other databases. So here, basically, we are inserting the documents into Elasticsearch. Now we can use Elasticsearch to provide some example, like what is the Artificial Intelligence Act? Remember the question that I gave to ChatGPT? And of course, since we are talking about a database, the results is a set of possible documents that contains similarity between the question and the answer. And I get the 3 documents. By default, LangChain takes the top 3 documents. If you want, you can even change the number. So we have these documents here. And if you see inside, is the meaning of our documents that are relevant to answer the original question. Okay, now that we have everything, we can finally connect the LLM. So we can take these results and put the results into LLM. So I'm just, again, using LangChain. The question is, what is Artificial Intelligence Act? So now we are passing everything to ChatGPT. This is the query. The result is the Artificial Intelligence Act is proposed a regulation framework, blah, 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 blah. One of very, very key important feature of this system is can give you the source where the answer came. And this is mind-blowing for an LLM, because LLM is not possible to get this information. So here I can say, look, these results came by the fact that I was able to digest page number 6, page number 10, page number 2, page number 0 of these particular documents. So basically, we solved the problem of the source of information. So we can now check if the answer is correct or not correct, because we have the source where the model used it. And this is very, very powerful. And also for a business point of view, if you have a database, you want to provide a system in your company to query natural languages, all your information, you can have the link of the document, the number of the page where the information came. So if you think carefully, this is basically the real semantic search we was looking for years. We have now all the tools to implement this kind of real semantic search in natural languages. And by the way, I give example in English, but the same work for Italian, German, French, because this model doesn't care about the language. It's about pattern matching strings, so you can even mix a language itself, even if they are not very performant, because, again, there is a more long discussion about this. But anyway, you can even ask in Italian, give the answer in English, and vice versa. So it's not so important for this model. Another example, another question, what is the pyramid of risk in Artificial Intelligence Act of European Union? Again, this is the answer. These are the pages where the document came. So, quite impressive. Few lines of Python code, open source, and everything works magically. So, apparently the demo works fine, so I'm very surprised about this. And again, the slide will contain the links, so you can have a look. And thank you a lot for your attention.
All right. Thank you for your presentation.